Let's start with the standard open Möbius band. In non-oriental surface geometry, it's the foundational object we use to study boundaries and edge identifications. When analyzing the spectral behavior of this surface, we evaluate the twisted Laplace-Beltrami operator. Specifically, we examine the anti-periodic sector, where a function's value perfectly inverts as it completes a single traverse of the band. On a flat strip, Euclidean geometry gives a metric of ds² equals dy² plus dw². This establishes a baseline ground eigenvalue. By fixing the meridional period L to pi times r, it resolves exactly to 1 over r². On a surface with constant curvature, the scalar curvature is exactly 2 over r². The flat strip eigenvalue is exactly half that amount. To study the open analog of closed curved surfaces, we have to alter the geometry of the space. Instead of building the band from a flat plane, we construct it by excising a spherical band from a totally geodesic 2-sphere within a 3-sphere. We take this excised spherical band and apply a specific mathematical pairing to the opposite edges. The edge at y equals 0 is identified with the edge at y equals pi r, while the w coordinate is inverted, generating a non-orientable quotient space. Inheriting its metric from the covering 2-sphere, this surface carries a constant positive curvature. This doubles the ground eigenvalue from the flat baseline, shifting it from 1 over r² to exactly 2 over r², perfectly matching the surface scalar curvature. The inherited curvature actively dictates the spectral bounds of the operator. To prove this exact value, we establish an upper bound and a lower bound through geometric deduction, verifying that they meet at absolute equality. This is the specific metric inherited from the spherical covering space. ds² equals dy² plus cosine² of y over r times dw². The w parameter measures the arc length along the reference great circle, while y tracks the position along each orthogonal meridional geodesic. We constrain our analysis to functions that depend only on y. This creates sector A, the reduced W-constant admissible regular branch anti-periodic sector. Within sector A, the Laplace-Beltrami operator takes a one-dimensional form. We calculate the second derivative with respect to y, minus a first derivative term scaled by 1 over r times the tangent of y over r. To calculate an upper bound for the ground eigenvalue, we evaluate this operator using a proposed ground eigenfunction, sine of y over r. The first derivative of this test function is 1 over r times the cosine of y over r, and the second derivative is negative 1 over r² times the sine of y over r. We substitute these derivatives back into the customized operator. The tangent and cosine terms cancel out, leaving two identical negative sine terms scaled by 1 over r². Those terms collapse into exactly 2 over r² times our original test function. We verify that this function satisfies the anti-periodic boundary conditions, as shifting the input by pi r accurately inverts the sign of the output. Integrating the square of the gradient over the square of this test function yields the explicit Rayleigh quotient for the surface. This direct algebraic substitution creates a hard mathematical ceiling. By computing a valid eigenfunction, the ground eigenvalue cannot exceed 2 over r². To prove the lower bound, we have to resolve a structural flaw in the quotient space. The inherited metric contains an interior singularity. This chart plots the Sturm Liouville weight, the absolute value of cosine of y over r. Exactly halfway along the meridian, at y equals pi r over 2, the metric coefficient drops to 0. On the physical geometry of the Möbius quotient, this vanishing coefficient means the transverse width of the band is metrically collapsed into a single point. Unlike the smooth north pole on the covering sphere, this creates a genuine interior cone point, characterized by a severe angular deficit. In Sturm-Liouville theory, this is classified as a limit circle endpoint. Square integrability alone isn't enough to define a unique operator here, so we must impose a specific boundary condition. We applied the Friedrichs extension. This condition dictates that any valid function must possess a finite Dirichlet integral, systematically filtering out solutions that blow up at the singularity. A Frobenius expansion at the singular point generates two possible mathematical branches. There is a regular branch bounded by a constant, and a logarithmic branch that scales with the natural log of the distance to the cone point. The logarithmic branch fails the finite integral test, The Friedrichs extension rejects it entirely, leaving only the regular branch. The defining property of this regular branch is that its derivative approaches zero linearly, scaling as big O of delta, the distance to the singularity. Using this scaling property, we implement a cone-point excision strategy. We mathematically cut a microscopic boundary around the cone point, defining a smooth, punctured manifold called M epsilon. The calculated boundary flux across these shrinking excision curves relies entirely on the linear scaling of the derivative. Because the derivative and the excision radius shrink together, the total flux scales with the square of epsilon. As the cut shrinks to zero, the boundary arrow vanishes entirely. The singularity does not contaminate the global spectral bounds. With the cone point safely excised, we build the lower bound using the two-dimensional Bochner identity. We substitute the properties of our specific space, replacing the Ricci tensor with the constant positive curvature k, which introduces a k minus lambda term. Integrating this formula over the smooth, excised manifold invokes Green's identity and exposes a boundary flux term for the exterior edges of the strip. To evaluate this integral, we examine the exterior boundaries of the Möbius band at w equals plus or minus w. Because this surface was cut directly from a totally geodesic sphere, the boundary curves themselves are geodesics within the intrinsic geometry of the surface. The defining geometric property of a geodesic boundary is that its geodesic curvature, kappa sub g, is exactly zero. We enforce a Neumann condition at the boundary edges. Combined with zero geodesic curvature, the boundary flux integral completely vanishes. The remaining complex term is the Hessian tensor. We apply the trace inequality, establishing that the squared norm of the Hessian is greater than or equal to half the square of the Laplacian. We substitute this back into the integrated Bochner identity, reducing the entire system to a clean algebraic inequality. We established our curvature k is exactly 1 over r squared. The arithmetic dictates that lambda must be greater than or equal to 2 over r squared, an absolute mathematical floor constructed independent of our initial test function. Two independent mathematical limits emerge. The Rayleigh upper bound places a strict ceiling at 2 over r squared. The Bochner lower bound establishes an identical floor. These bounds perfectly compress. The ground eigenvalue is exactly 2 over r squared, equaling the scalar curvature. For these two bounds to meet at equality, the trace inequality utilized in the Bochner proof requires a highly specific geometric alignment. The alignment condition demands the Hessian tensor must be strictly proportional to the metric itself. Calculating the three diagonal components of our test function's Hessian against the Christoffel symbols confirms this proportionality holds across every smooth point on the band. The flat strip forms the analytical baseline, but the constant positive curvature inherited from the spherical quotient space acts as the structural multiplier. It doubles the eigenvalue, perfectly resolving the open surface analog to the closed projective plane.